Resonance and mechanical resonance in physics. So what is resonance? Resonance occurs when an object vibrates at its natural frequency, and this results in an increased amplitude of oscillation, or a sudden spike in its harmonic motion. So for example, if you think about when you're pushing a child on a swing at the right timing. Now sometimes when you push on the swing, it'll actually interfere, but if you push at the right time, the child's arc, the swing arc, will drastically increase and they'll kind of keep going in that harmonic motion. And so when we speak about natural frequency, remember that every object has its own natural frequency of vibration when it's being disturbed. For a pendulum, it depends on the length of the string and not the mass, which we talked about last class. Natural frequency is the frequency at which an object will naturally oscillate, and again, that's when it's disturbed. So, if you think about it though, how might changing a pendulum's length affect its natural frequency? So if I made the string longer of a pendulum, how would that change the way it behaves once it's been disturbed? Well, remember that longer pendulums swing more slowly. So the pendulum will have a lower natural frequency if its string is longer. Now, one of the key players in resonance is something called the forced frequency, and it's as key as the natural frequency is. Forced frequency is an external force that is applied to an object, and it can maintain or increase the amplitude of oscillation, meaning the degree at which it goes back and forth. When force frequency matches the natural frequency, resonance occurs, which is that sudden spike in amplitude. So if you look over here in the graph, the green line would be where your forced frequency has matched your natural frequency of the object, and when it matches that natural frequency, you get a large spike in the amplitude. Now, damping is just referring to the energy that is lost as an object oscillates back and forth in this simple harmonic motion. And so not only do we see an increase in amplitude, but we also see a decrease in damping. So mechanical resonance, which is a very specific type of resonance that occurs in physical systems, occurs when the force frequency exactly matches the natural frequency. And so you time it just right where you apply a force on the pendulum system, for example. This can lead to a large increase in amplitude, and it's potentially destructive in some cases, especially bridges in highly windy areas. So why might mechanical resonance be a concern for engineers? Well, we've seen this with bridges, where when it's put over a large water body and there tends to be a lot of wind and storms that occur, if the wind frequency, right, which would act like a force frequency, matches the natural frequency of the bridge, then the bridge itself can undergo mechanical resonance and flip back and forth like it did in the Tacoma Bridge from this image that you see right here. Here we have what is called a coupled pendulum apparatus. Both masses are the same, and it's connected through the same string, or in this case, elastic band. And what's going to happen is the energy will transfer from the initially moving pendulum to the stagnant or stationary pendulum. As the energy is transferred, the amplitude of both pendulums increases until they swing in unison, like you can see over here, showcasing resonance. The pendulums oscillate together at their resonant frequency, which is also their natural frequency. Every time the first pendulum swings, it pulls on the connecting string and gives the second pendulum a small tug. Since the two pendulums have the same string length, the pulls of the first pendulum on the second occur at exactly the natural frequency of the second pendulum, and so that adds to the amplitude and it begins to swing too.